All right. So what I'm going to discuss next is the most important key issue. All right. This is the point where we have to compare among the 4 field quantities. Let's start with electrical dipoles. This is something we know better, right? So if I have one single pair of induced electrical dipole, electric dipole is always defined pointing in the direction from the negative charge to the positive charge. All right. So if this is the direction of my induced electric dipole, where should my applied external E field be? In which direction? Usually parallel to P, right? So my externally applied field is also in this direction. Okay? Now, assume I know that, well, externally applied fields are generated by free charges. Okay? So I can write or draw lots and lots of free charges. So these are free charges. Free. Free means they're free to move around, not because you don't have to pay the money, okay? Right? So these white lines are the E field lines generated by the free charges. Along the way, you have a piece of material, and this material decides to generate one single electric dipole. This is induced by the presence of your externally applied E field. But as we all know, once you have the induced electric dipole, it emits its own E field lines, right? So you have for example, well, the E field lines always start from the positive charge and ends on the negative charge. So then you ask yourself, well, in this material with a permittivity of epsilon, the absolute permittivity of epsilon, which field quantity can tell you the maximum number of field lines? Let me ask a question again. So if I only care about, so on this single axis, I'm trying to plot the number of maximum field lines. Okay? And this is associated with row free, and this is associated with row total. This is related to J total, and this is related to, can I erase this part? J free. Okay? So now we have complete information on this part. For a material having electric response. Inside this material, if you count the number of field lines due to the total charge density, this is associated with E, right? E is the total charge. Then you expect to have a reduced number of lines, meaning the white one plus the yellow one. Some are being canceled out, right? So if you look at this particular space and you ask yourself, what is the maximum number of field line available? You only count the white ones, right? Okay, which means D will be greater than E, right? The number of field lines associated with D in this case is 1, 2, 3, 4, 5. 5. Right? Inside this material. And at the same time, you ask yourself, what is the number of field line associated with E? Well, in this case, 5 pointing upwards and 3 pointing downwards, making net 2 pointing upwards, right? So therefore, when you talk about E inside the material, the number of electric field line would be less than the number of field line related to D. And this is purely due to the fact D only takes care of the free charge density. But E has to take care of the total charge density. Okay? And for this reason, I recommended you to write dE equals D divided by epsilon, right? To capture the fact that inside the material, E is weaker as compared to D if you don't care about the mu zero. Okay? So this comparison is actually taking care of the number of field lines. Okay? Now let's draw the magnetic part. If we have some material as well, if I can generate a single pair of induced magnetic dipole in this material, okay? So in this case, your current is flowing, well, out of the paper on the left-hand side and into the paper on the right-hand side. So basically, this is giving you some magnetic field line pointing upwards, right? You still use your right-hand rule. So this is telling you, in this space, I also applied well, I should be using a different color. So the white lines are your externally applied current in generating its own field lines. Having the presence of your applied magnetic field inside this material, you produce one single magnetic dipole, right? The dipole itself also generates a current and generates its own field line. So now for this particular material, you ask yourself the same question. What is the number of field line related to the vector field quantity? B is related to the total current, right? The total current. So you can think of, well, each of this, I should be using the color. Okay, let me use the color. Each field line you can think of is being generated with a current loop, right? So in this case, if you think about B is related to the total current density. Then you have to sum up all these loops, the current conducted by all these loops, meaning you add all these field lines up, right? So in this case, you have B. The number of field lines associated with B is, in this case, higher as compared to H. H is only taking care of the free current density. Therefore, you're only counting the white lines. Okay? H. Right? So what is this dramatic difference? I'm intentionally trying to draw D and H on a pretty much the same scale. Okay? I'm trying to draw this to reflect the truth. D and H can be viewed as your applied fields. D is your applied E field, and H is your applied magnetic field. Over to the left, you're dealing with electric material. Over to the right, you're dealing with a magnetic material. Okay? When you apply external E field, you are actually sending a lot of electric field lines through this material by having free charges. But the electrical material generate induced electric dipoles, and the meaning because it generated the induced dipole is to give counteracting field lines. Okay? To make the material having weaker E field intensity. Right? But magnetic materials are dramatically different. So you have to sense. Side-by-side comparison tells you magnetic materials are very weird. When you apply external magnetic fields, you are also sending a lot of magnetic field lines through this material. Having this externally applied magnetic field lines produce magnetic dipoles. And the magnetic dipole also generates its own field line. But in this case, in the world of magnetism, you have the chance to have more field lines as compared to your initial applied field. What does it mean? This means in the world of electrics, you work, right? But you get very little paid. In the world of magnetism, you work, you still work hard, but you're getting paid even more. So guess, which type of student do I like to teach? If you were a teacher, right, you like to work with the students. You teach just by explaining one problem, and the student can learn 3 problems, right? 举一反三, right? If a list type is the student you don't want to teach, you spend 100% of energy teaching, but he or she only absorbs 50%, right? So think about it. This is a live comparison and very dramatic. This is telling you the world of magnetism will have its own benefits because you can apply weak field, but inside the material, you can create very strong magnetic responses. Meaning, you only apply for maybe 5 external field lines, but if you can generate lots and lots of induced dipoles, and they each give rise to maybe a number of induced magnetic field lines, this gap will be very large. All right? So now take a close look. Why by name are D and B called the same form, the flux density, while E and H are called the intensities? It's due to their physical meaning. If you want to ask about, in the space, what is the maximum number of field lines available, that would be answered by looking into the flux densities. So these two are called flux densities. And these two are called the field intensities. Okay? Is it okay for everyone? Side-by-side comparison. Assume you apply the same number of field lines for electric material and magnetic material. Okay, so these are both applied. But for the world of magnetism, in terms of B, you can achieve even more field lines, which is good. Right? You pay $1, you get $2 back. For electrical materials, the sad story is the number of field lines you send are always lost somehow. So in the end, the field intensity you get, the number of field lines really effective in that space, is always less. Okay? But still, you're asking, what is the maximum number of field lines available? Those are described by the flux densities. Right? Okay up to now? If it's okay for everybody, let me just move on to something more difficult. This is just to recapture what I drew on the blackboard. Okay? Over to the left, we have electric materials. Over to the right, we have magnetic materials. First thing first, something you have to note and absorb for the rest of your life is when we're dealing with magnetic materials, we have the chance to increase the number of magnetic field lines. This is dramatically different as compared to electric materials. For electric materials, basically the number of effective field lines is always decreased as you generate the induced electric dipoles. But for magnetic materials, some magnetic materials, once you generate the induced dipoles, it can further enhance or increase the number of magnetic field lines. Okay? So please do remember this picture. Please do. This is your applied field, but in magnetism, you can actually earn something. Electric world, you always lose something. Okay? So the main point is this. The induced magnetization can increase your magnetic flux. The magnetic flux is nothing more than the number of field lines in certain area. Okay? So this is a very important figure for you to remember and understand. Okay. All right. Now, this is walking back into history. Right? We started this semester by introducing E, and then in magnetism, we introduced B. So this is the entire semester up to now in front of you. Everything that we learned. E is the E field intensity. Mathematically, it is expressed by the D minus P. P is your dipole moment, dipole vector. B now is related to the total current density, and therefore H plus M. So when you compare these two field quantities side by side, mathematically you don't see any similarity, right? B is having one field quantity plus another field quantity, but this one is something minus something. So they are very different. So why? Ask yourselves, why is the textbook introducing E first for the world of electrics and B first for the world of magnetism? Why? The answer is very apparent. The answer is E is associated with a total charge density, while B, although it's a flux density, mathematically it is quantified by the total current density. And for this reason, the textbook is introducing E and B first, due to the physical meaning. This is related to the total current density, and this is related to the total charge density. So even though their names are different, one is intensity, one is flux density, mathematically they are different, but in physics, in the physical meaning, they are similar. Right? Okay, then in materials, right? For electrics, we introduced D, the flux density. Flux density is your E field intensity adding the induced dipole moments. H is different. It is B divided by something and minus something. Okay? So now you have the four field quantities in front of you from the mathematical definitions. And ask yourselves, the most critical moment is now. Are you able to differentiate their differences or find their similarities? I'm actually using the colors to help you, right? Mathematically, E and H, they're both called field intensities, and therefore mathematically they have the same form, D minus something, B minus something, right? D and B are both called the flux densities. So therefore, their mathematical formula are similar. Two vector quantities added together. Two vector quantities added together. Okay? This is the most confusing part. Okay? So I'm really hoping by spending almost 50 minutes, you really appreciate the similarities and differences. Okay? Mathematically, the field intensities have almost identical mathematical form, and the flux densities have identical mathematical forms. But sadly, the physical meaning is reversed. E is related to rho total. B is related to J total. Okay? So this is the reason why I spent this moment to explain the amount of field lines. Okay? So somehow you have to merge together this slide together with this picture. You have to absorb everything to really appreciate and being able to tell which one which. Okay, so now, again, this is just to recap what we wrote on the blackboard. D is related to the free charge density. H is related to the free current densities. Okay? So basically, I mean, for the entire semester, we're only trying to introduce these 4 field quantities. So now we have 3 minutes left. Please do take a good look on everything covered on this slide and on this blackboard. Basically, this is the most critical moment for you. If you have questions, feel free to raise your hand and ask me. You can ask me in Chinese or English. Okay for everyone? I'm very surprised. You're super smart. Okay? You're the smartest students I've ever taught. All right? If it's okay for everybody, let's try to quantify. Let's try to quantify the relationship between B and H. Okay? Just like what we did for D and E, you can view this H as our externally applied magnetic field. You generate lots and lots of magnetization vector, lots of dipoles. So this is assuming your generated magnetic dipoles all line up with your external field lines. So you have a linear relationship, right? The stronger your applied field is, the more magnetic dipoles you generate. So this is assuming a linear relationship, and you're also assuming this material is very uniform. Okay? Now we replace this relationship into this definition, right? So now B and H is basically just linear, right? So this is viewing the material in a macroscopic sense. I don't really need to know what's happening inside locally. All I need in the future is, well, this is certain magnetic material. For example, iron or steel, steel 304. Somebody already measured this constant for me. Then in the future, I can only say, oh, for this typical material, it has its own relative permeability, or mu0 multiplied by the relative permeability is called the absolute permeability. just like epsilon r and epsilon that we defined previously. Okay? So mu r is a relative permeability, and mu is your absolute permeability. So in the future, relax, okay? I'm not going to test on your microscopic view. So in the future, I give you, okay, this material has either mu r or mu. You know how strong it can generate the induced magnetic dipole moments. Okay? So everything is now encapsulated by the single perimeter. Now, for this case, again, I want to emphasize it is better to write the relationship for D and E using this form, right? To remind you, this is your externally applied E field. Inside an electric material, your E field intensity is always weakened. The number of field lines is always canceled by the induced electric dipoles. Okay? So if you have a very huge epsilon value, meaning you have lots and lots of induced electric dipoles, you have very weak E field intensity inside the material. But on the other hand, as we talked, for magnetic materials, hey, it's a chance to win free tickets, right? Free lunch. You apply very weak external magnetic field, meaning you send in maybe 5 magnetic field lines, but then this magnetic material produces a lot of induced dipoles. And each magnetic dipole additionally gives you some free field lines. So in the end, you enjoy free lunch, right? You pay $10, you eat a buffet, right? So these two are the main essential field relationships that you have to remember, okay? So I spent 50 minutes just to clarify the fact behind this two. You can have more magnetic field lines by using magnetic materials. You choose the right magnetic materials, you can have lots and lots of free field lines. But for electrics, no matter what you choose, you always have reduced number of field lines.